Okay, guys, we're ready for the next person, and that is Niels von Wardenburg. He studied and has an MD in human medicine, and he's currently working as a neurologist and a clinical scientist at the Charité University Medicine. Part of this work is for the Excellence Cluster of NeuroCure. His research focuses on the development of innovative cell therapies for the treatment of neurological autoimmune diseases. The title of his talk is Medical Progress in 3 Acts. Is the time ready? Time? Yeah? Stage is yours. Big applause for Niels von Wardenburg.
Hello everyone, I'm Niels, I'm a neurologist, and I'm very happy to be here today. And just a brief disclaimer, the whole story is made up. So the story is not true, but the science is true. I would like to take you on a journey through time today. We will hear the fate of the 25-year-old Zoe, and each time it has a different ending. So the journey through time is entitled Medical Progress in 3 Acts. So let's start with the first act in 2005. Zoe is planning her vacation. She's a medical student at Charité University Hospital, and she wants to travel to Spain with her boyfriend Alex. And during the planning, she has increasingly difficulties with concentration. And one evening, they want to meet in her favorite restaurant, but she doesn't show up. And Alex gives her a ring, but she doesn't pick up. And what's he doing? He drives to her apartment, and rings the doorbell, but also there, she doesn't open. So luckily, he has a key. He enters the apartment, and he finds her in a completely devastating situation. She's yelling at him, "Who are you? What are you doing?" And all of a sudden, she has an epileptic seizure. And Alex is calling the ambulance. The ambulance is bringing her to Charité, and there she has several seizures in a row. So the doctors have to put her into artificial coma, and she's admitted to the neurological intensive care unit. And there, the attending neurologist, Dr. Hoffman, is doing the regular diagnostic procedures, so an MRI scan, laboratory tests, and he suspects a viral brain inflammation. So he starts treatment with acyclovir, an antiviral drug, but unfortunately doesn't work, so the viral tests are negative, her situation deteriorates, and very sadly, her condition deteriorates and she dies eventually. That's hard, I know, but I said it's made up, but it could be true. So like, it happened 20 years ago. Now, Act 2, we are now in 2018. It's the same situation, but this time Dr. Hoffman has, after a few hours, the lab results that virus encephalitis is not the case. So the tests are negative early on, and he knows there is an alternative disease showing with the same clinical picture, and it's called NMDA receptor encephalitis. It's an antibody-mediated disease that is caused by antibodies against the NMDA receptor, a very important receptor in the hippocampus and else in the brain. And antibodies are produced usually by B cells, and they protect us from pathogens such as bacteria, viruses, fungus, and so on. But in certain situations, caused by an ovarian teratoma or herpes simplex virus infection, or unknown reasons, make those B cells produce antibodies against the NMDA receptor. And Dr. Hoffman, he starts an immunosuppressive treatment, so a treatment that is kind of stopping the immune system to attack the own brain. And this is really like it's functioning well, but it has a downside that, one, it's not perfectly effective, and secondly, she has several infections, Zoe, and she's on the ICU for several months. She will return home, so she survives, but her brain is so damaged that she cannot continue her studies. Coming now to this third act, we're traveling now into the future, 2030. Same situation. We find, or Dr. Hoffman finds the NMDA receptor antibodies in the cerebral fluid of Zoe. And colleagues and me, we thought about how can we improve the function of the treatment and on the same side reduce the side effects such as infections, like life-threatening infections. And we took a piece of the NMDA receptor, and we set it onto T cells, and T cells are very good at killing cancer cells, infected cells, and so on. And we named those cells chimeric autoantibody receptor T cells. And those T cells detect specifically the disease-causing NMDA receptor reactive B cells. They secrete cytokines and other molecules and induce apoptosis of the cells. That means that those cells die. And we tested whether this is really working. So we made those NMDA receptor antibody-producing B cells glow, injected them into mice, and treated them with our AA CAR T cells. And as you can see here, on day 20, there is no glowing in those animals, so no NMDA receptor reactive B cells are left. And in 2030, Dr. Hoffman starts the treatment with the chimeric autoantibody receptor T cells. And this time, Zoe can travel to Spain finally. She takes some literature with her, namely about CAR T cells and NMDA receptor encephalitis, and she decides to dedicate her professional life to research, as I do. Thank you so much.
Niels von Wardenburg.